we are going to discuss about CPU scheduling. We are going to look at different scheduling algorithms in this chapter. So now let's look at the basic concept of CPU scheduling. Maximum CPU utilization can be obtained through the multi-programming in such a way that multiple programs can run concurrently, so you can have maximum utilization of your CPU. CPU input-output bus cycle. Process execution consists of a cycle of CPU execution and input-output wait. Then CPU bus distribution, that is the bus time distribution of the CPU. These are the basic concept of CPU. So as we look at earlier on in our classes of process life cycle, we've looked at the stages of which we discuss about the waiting stage. So waiting stage is waiting for input-output request. So now we are going to look at the alternating sequence of CPU and input-output bus, that is the execution. So we have looked at the operations of the running state, where we say the operations of the CPU, we have the load, we have the add, and we read and write. So if you look at it now, we have a command of load store, add store, read from file. So these are the operations that took place in the CPU, that is the execution. Then when there is input or output waiting, then we have the input output bus, that is the request. Now is waiting for request to occur or for request to be responded. Then we have store increment indexed, then write to the file. So if you look at, these are the sequence of read and write, or we have the sequence we said from the running state to the waiting state. This is what give a clear example, that is the alternating sequence of read of the waiting state and the execution state. So now let's look at the CPU scheduler. The CPU scheduler is responsible for selecting processes from the memory, that is the random access memory, which are at the ready state, to move them to the CPU for execution. So that is the main function of the CPU scheduler. CPU scheduler decisions may take place when a process, in the first way, is when it switches from running stage to waiting stage. Because when a process is from running state to waiting state, it have to go back again to ready state. So therefore, that is when a scheduler will now decide which process will go to the CPU for execution. Also, it can take place from this when it switch from running state to ready state. It's also possible it goes back to the ready state. Also, when it switch from waiting state to the ready state and then to terminate, that is from the running state to terminate, it can switch them all in these processes. We have scheduling under 1 and 4 non-preemptive. We also said all other scheduling is preemptive. When you look at, we said preemptive and non-preemptive. The word for preemptive is a scheduling algorithm that allow a process to be preempted or to be halted before it finishes execution, or to be interrupted. That is the word of preemption. The non-preemption, this is a situation whereby a process will not be interrupted or will not be replaced by another process until the process gets finished execution. That is the preemption and non-preemption. So there is also another part of it, which is the dispatcher. The dispatcher gives control of the CPU to the process selected, because the scheduler will select a process, then the dispatcher will now take control of the CPU for the process that is being selected by the short-term scheduler. And the short-term scheduler is the ready state that we know. This involves switching context, that is where we look at the switching from this state to another state. We also have switching to user mode, jumping to the proper location in the user program and to restart the program. We also have dispatch latency. This is a time that is taken for a dispatcher to stop one process to start another process. Let's look at the criteria of scheduling. We have the CPU utilization, which keep the CPU as busy as possible. That is how you utilize your CPU. It makes maximum use of your CPU, that is the CPU utilization. We also have the throughput, of which processes that complete their execution per time units. that is the amount that a process complete its execution per time unit. Then we have the turnaround time, amount of time to execute a particular process. That is the time that it takes a process to be executed from the ready state to the termination state. Then we have the waiting time, the amount of time a process has been waiting in the ready queue for it to be selected or for it to enter into the running state. Then we have the response time, amount of time it takes from when a request has been submitted until the first time it responds to it. That is from the running state to waiting state. So the time that it takes for it to be responded at that waiting state to go back to the ready queue, this is known as the response time. That is the time that you take to respond to the input-output request. So we all talk about the CPU. We are looking at the optimization criteria. Maximum optimization of CPU, that is in the terms of utilization. That means you don't supposed to leave your CPU to be idle. Also maximum throughput, minimum turnaround time, because when you look at turnaround time, you are looking at the time that it will execute the process. So the process should not take long time to execute. That is why we need to get minimum turnaround time. Also, with a good scheduling algorithm should have a minimum waiting time. Therefore, it will enable the process to go back to the ready queue and continue with its execution. Also, it should have a minimum response time, which also determines the time that a process will take before an input-output will be responded to it. So it also requires a minimum response time. But the CPU utilization should be maximum as possible. Throughput also should be as maximum as possible. Now we will start by first scheduling algorithm, which is the first come first serve scheduling algorithm. This is a scheduling algorithm that works based on first come first serve as it implies. The first process that happens to be in the ready state will be the first process that will access the CPU. So that is the way it says first come first serve. So if you look at this place here, we have process 1, process 2, and process 3. We have their burst time, which is their execution time, 24, 23, and 3. So if you look at it, their arrival time, the process 1 comes first, process 2, then process 3. Suppose that the processes arrive in order, that is 1, 2, 3. That means process 1 have the first time, process 2 comes at the second time, then process 3 comes at the third time. Now here we have what you call Gantt chart. This Gantt chart is there to show you the time that is the completion time of each process. So now we have process 1 comes at 0 second, that is millisecond, that is why we have the 0 here. Then we have P1, which have execution time of 24 seconds. That means the time it takes to execute is 24 seconds. Then you write your 24 at the end. That is where the process 1 finish its execution. Then we now have process 2. It enters immediately after process 1 finish its execution. Let me give you an example of ATM machine. When you go to ATM machine, many people can go to ATM machine, but usually we ask, who is the last person? Then you follow the queue. It's just like a queuing policy. You follow the queue. So when you are following that queue, it means you are following the last person that came. So also it happens in this first come first serve scheduling algorithm. It also applies a queuing policy, which is in data structures. So the moment process 1 finish execution, process 2 will now enter. And when process 2 is entering, process 2 have 3 burst time. That is the execution time of process 2 is 3. So when you add 3 plus 24, that is the time that it wasted waiting for process 1 to finish its execution plus a time of execution. It will now give you 3 plus 24 will give you 27. So that is when the process 2 will finish its execution at 27. Then process 3, immediately process 2 finish its execution, process 3 will now enter into the queue, whereby it will start at 27. Then it also have execution time of 3. Then it wasted 27 seconds waiting for process 1 and process 2 to be executed. And it also enter with 3 seconds of execution. Therefore, it will end or it will finish with 30 seconds of execution. Then we look at the waiting time. Process 1, the waiting time of process 1 is 0 because it doesn't wait for any process to be executed. Then the waiting time for process 2 is 24 because it waits for process 1 to execute, then it's execute also. Then process 3 waits for 27 seconds for it to be executed. That is the waiting time of process 3. Then the average waiting time, you now sum the waiting time of all of them, divide by 3, then it will now give you the average waiting time. So now here we have another scenario whereby the processes arrive at different time. Here the process 1, the process 2 come first, process 3 followed by process 2, then process 1 comes last. So that is why suppose that the processes arrive in this order. In some questions you will find a question coming with a table giving you the arrival time, the process number, the process name, also it will give you the burst time, that is the completion time. So now when you look at it like this, you can be able to identify the burst time of each of these processes based on the Gantt chart above. So the waiting now, process 2 enters and it waits for 0 seconds. Then the execution of process 2, the burst time of process 2 is 3. That is why it completes at 3. Then process 3 now enter. When process 3 enter, the completion time of process 3 is 3 also. That is why we are having 3 plus 3 will give you 6. But process 3 wait for 3 seconds before it executes. Then from there process 1 enter. Then the execution time of process 1 will be 26. That is why when you put 24, when you put 24 plus 6 will give you 30. But process 1 wait for 6 seconds before it execute. So let's look at the waiting time of process 1 is 6. As I told you, it wait for 6 seconds before it get execute. Then process 2 wait for 0 seconds, while process 3 wait for 3 seconds. This is also how you will get the average time. That is saying 6 plus 0 plus 3 divided by 3 will now give you 3. So that is, it will give you 2, sorry, instead of 3 it will give you 2, because when you divide 6 by 3 it will give you 2. Sorry, take note of that mistake there. So that is that. So much better than the previous case. So that is how you find the effectiveness of a scheduling algorithm. Then we have the second scheduling algorithm, which is short job first. This short job first, it associated with the process length, that is the burst time or execution time. Use this length to schedule the process with the shortest time. For example, now there will be a situation or scenario whereby a process, if it's following first come first serve, maybe first process will come with maybe a lot of burst time, like the previous case we look at. Process 1 having, let's assume process 1 is having 24 seconds to execute, while process 2, 3 are having 1 execution burst time. Therefore, these two processes that are having less execution time will have to waste their time waiting for the process 1 to finish its long execution. So the short job first is a scheduling algorithm that try to avoid the waiting time, to minimize the waiting time of a process. It's also a non-preemptive, which means once CPU gives a process, it cannot be preempted until it completes the execution. So let's look at the example of short job first. All right, now look at this example. We have process 1, 2, 3, 4, and their arrival times respectively, ranging from 0 to 5 seconds. Then the burst time is 7, 4, 1, and 4. So now this is we said is non-preemptive. That means once a process enter, it will not be preempted until it finish its execution. So one of the things is that all of them would, the first process will be the one to enter first, the one that arrive first. That is the criteria. But after, it will now apply the short job first. Instead of process 2 to enter, process 3 will enter, because it will check from process 1 to process 2 to process 4, which one is having the shortest execution time, which is the burst time? From there we can see that process 3 is the one having 1, which is the burst time, or 1, so it will be the one to be executed first before any other one. Then we'll have now process 2 and process 4, which are having the same burst time. In this situation where you are having the same burst time, you will now apply the principles of first come first serve. That is why we are executing process 2 before process 4. Also the formula to calculate the arrival time will be as same, whereby we will say the waiting time of process 1 will be 0, because there is not any process that it wait for. Then process 2 wait for 6 seconds before it execute. Process 3 wait for 7 before it execute, and process 4 wait for 6 seconds before it execute. This is where we have 6 plus 3 plus 7 divided by 4, which gives you 4 as the average waiting time. So now we have looked at 2 scheduling algorithms, where we look at the first come first serve and shortest job first. These are 2 scheduling algorithms, but we are going to look at more other scheduling algorithms in our subsequent classes. We will look at the round robin, and we will look at the priority scheduling algorithm. So this is the end of today's class. If you have any question or your request for more examples, you can please go online, and if you have any challenges regarding any question you find, please get back to me. I will now respond to your questions. Thank you very much.